It's recording, right? So actually, humidity is the last lesson of what? Heat. So, but the thing is, you don't need to know a lot of heat to understand. It's tiny bit you need, but not much. This lesson is normally considered as a hard lesson for children. I don't know why, but they consider this as what? A hard lesson. But it's something very beautiful. It requires your imagination a lot. You need to think, visualize. And, as I always tell, everything that is supposedly complex is made up of what? Simple things. So if you understand the simple things, you can understand what? The complex things. Okay? Right. So then, have you all noticed that when you wake up in the morning, right, and when you go to the mirror, have you all seen some dew depositing? Have you all seen
Yep,
that?
see, there's a lot of it around here
Yes. So we're going
outside the
to
door.
ask, yeah, we are going to ask reasons as to why. Okay, so normally when it cools down, what happens? The water vapor deposits. And then the question is why, right? And we're going to ask those questions once we cover up the lesson, right? Okay, so I'm going to share the screen then. So anyway, when you are learning about humidity, there's this important question to ask. Now, what is vapor pressure, right? What is vapor pressure? Pressure means force over area, right? So force acting on a perpendicular area, that's the pressure. But what is this vapor pressure? The pressure that the vapor creates. But where is the vapor? Let's think of a container, right? So if you think of a container, what do you see? You consider a container, there are these vapor molecules that will go and strike what? The vessel walls. Then what will happen? Think of those vapor molecules going and striking the vessel walls. When the vapor molecules go and strike the vessel walls, they bounce back, right? They go and bounce back. When the vapor molecules go and strike the vessel walls and bounce back, there is a momentum change, right? There's a change in momentum. The momentum vectors are in opposite directions, right? So when these molecules, when they go and strike the vessel walls, there's a change in momentum that happens in unit time. So what will happen due to this change in momentum in unit time? Yeah, there's going to be a force. Rate of change of momentum is the force. So when these gas molecules bounce and come back, when they bounce the vessel walls, there's going to be a momentum change in a particular amount of time. And then there is a force. When there's a force acting on a particular area, there's pressure, right? There's a pressure. Okay, so that's what I just described in here, the momentum of air molecules. So momenta is the plural. It means so many different, tiny molecules have different momenta, right? Momentum is the momentum of a single particle. So the momenta of the vapor molecules change upon striking the vessel wall, right? That I explained. Forces are generated due to this change in momentum. When these forces act upon the vessel wall, pressure is generated, right? Understood? So is this video being recorded?
Yes, sir. It's recorded.
Okay. Okay. I think that part is clear, right, with everybody?
Yes,
Yes,
it's clear.
clear.
Okay. Now, then the next question is, what is vapor density? What is density? We talk about volume density. What's volume density? Mass per unit volume. Actually, there are different types of densities. For example, there's another density, linear density. That's the mass per unit length, right? If you have a rod of mass m divided by the entire length of the rod, you get the mass per unit length, right? That is the linear density. So what is vapor density? What is vapor density? Mass of vapor in a unit volume, right? If you have a mass m of vapor in a volume v, then the vapor density is what? M over v. Now, what is saturated vapor? What do you mean by the word saturated?
There's a lot of it, like concentrated, something like that.
Yeah, something like that. Now you
Maximum.
say, very good. Yeah, so those ideas. You see, like we are saying, you're saturated with thoughts, no? Problems, right? So you're kind of full. That's the idea. Okay, so what is saturated vapor then? If the vapor is in dynamic equilibrium with its homogeneous liquid, then that vapor is said to be saturated. It's like this. Now, if you consider a container and if you have some water, you know, like the amount of liquid in this closed container does not change, right? So the liquid in here is in equilibrium with what? The vapor, right? The liquid, let's say X liquid is in equilibrium with what? X gas, right? So there is an equilibrium. Is that clear? There's an equilibrium. And we say this dynamic equilibrium, right? If one molecule becomes a liquid molecule, if a gas molecule becomes a liquid molecule can become a gas molecule, right? So there's this dynamic equilibrium and the concentrations remain the same. So now, I mean, assuming other factors are constant, right? When other factors are constant at that particular instant, if you look at it, the concentration does not change. If other factors are constant, we are going to have a constant amount of water vapor. Okay, so what is saturated vapor then? So when the vapor is in dynamic equilibrium with its homogeneous liquid, then that vapor is said to be saturated. So remember, whenever you see a liquid in equilibrium with its vapor, what are we looking at? Whenever you see a liquid in equilibrium with its vapor, you are looking at saturated vapor. You're looking at saturated vapor. Okay, right. So then, like the other intuitive idea of what saturated vapor is that if this think of a particular space of volume V, think of a space having a volume V, right? Let's say the maximum amount of water that I can have in there, water vapor that I can have in there is M. So there's a particular volume V, right? In this particular volume V, the maximum amount of water vapor that I can have is M, right? That means this environment is going to be saturated with a mass M of water vapor. If I have a mass less than that, that means what? It's going to be unsaturated, which means I can saturate it, which means I can add more water vapor into it, into that closed volume V at constant temperature, right? Is that clear? So what is meant by a particular space being saturated is that the space of interest has the maximum amount of vapor that it can bear in the considered volume at the considered temperature. Because the important thing here is that you have to maintain the temperature and the volume the same if you want to bring about this argument. Because the amount by which you can saturate a particular space depends upon the temperature and the volume. If you change the temperature, the amount by which you can saturate a particular space changes. If you change the volume, the amount by which you can saturate a particular space changes. So we'll see how actually, right? So now just think of increasing the temperature, right? So think of a space, think of a particular space, think of fixed volume, right? And if you think about this volume V, think of those molecules, vapor molecules that we have. Now let's say it's already saturated. That means I have in here the maximum what? Amount of water vapor molecules that the system can bear, right? Now tell me, what if I increase the temperature? Now molecules are moving very fast, right? Molecules are moving very fast. It feels as if there's some space for molecules now. Earlier, at a lower temperature, the movement of the molecules were slow, right? Slower. But now you increase the temperature, which means a particular vapor molecule is not going to stay at a point for too long. So it feels as if there's more space. Is that clear? So this perception of
Yes.
space gives what? This perception of space gives more room for the addition of more water vapor, which means I can further saturate it. Earlier it was saturated. Yes, then I increase the temperature. At a higher temperature, what can I do? At a higher temperature, what can I do? At a higher temperature, I can add in more water vapor molecules, right? I can add in more water vapor molecules and then increase the saturated vapor pressure. We'll be talking about that. I hope everybody's clear with that. Now, think of this now. What would happen if I increase the volume? If I increase the volume, keeping the temperature constant. So lots of arguments today. So I'm going to keep the temperature constant, right? I'm going to keep the temperature constant. And what am I going to do? While keeping the temperature constant, I'm going to increase the volume. Now suppose this environment is saturated. That means whenever you see the liquid in equilibrium with the vapor phase, right? Whenever you see the liquid in equilibrium with the vapor phase, you are looking at what kind of vapor? Well, you're looking at saturated vapor. Now tell me, what if you increase the volume of this particular container? If you increase the volume of the particular container, what are we doing? When you increase the volume of the particular container, you are giving more space for the water molecules to be, right? So when you increase the volume of the container, there's more space for the water molecules to be. Therefore, what would happen? The vapor becomes unsaturated, right? Some of the liquid will also vaporize, right? And then, of course, you have what? A higher volume, which means you can contain more vapor, which means you are going towards a state of unsaturation, which means you can pack in more water vapor molecules, because when you increase the volume, you increase the capacity to store water vapor molecules. You increase the capacity, and the same thing can be done with an increment in the temperature. Higher the temperature, the greater the amount of water vapor molecules I can integrate into a particular space, a particular volume, right? Is that all clear? Right.
Yeah, sir, it's clear.
Now,
sir.
let's get into the rest of it. I think I just mentioned this already. So the maximum amount of vapor that a particular space can bear up, it also increases with the increase in temperature and volume. So if I increase the volume, I can bear up more vapor. The vapor pressure and the vapor density reach a maximum when the vapor is saturated. You're going to have a maximum density, right? That means it's going to be packed up, right, with those water vapor molecules. You have a higher concentration of them in a particular volume. So, which means the vapor pressure and the vapor density is a maximum. The more water vapor molecules you have, the more they will collide with the container walls, right? The water, when you have a greater number of water vapor molecules, that greater number will collide with what? The vessel walls. And then there will be a greater force generated overall, right? So now, and there's a very important point: saturated vapor pressure depends only on the temperature. It only depends on the temperature. Something very interesting to think about. And I want you all to think as to why and tell me an answer.
Is it because of the kinetic energy and stuff?
So now, if I get into it deeply, the idea is the mass per unit volume does not change. Because now think like this. Think there is what? A liquid here. And it's in equilibrium with the vapor, right? It's in equilibrium with the vapor. Now, what if I increase the volume? What if I increase the volume? Then what will happen? Maybe there's a little bit of liquid still remaining, right? Little bit of liquid still remaining. But the thing is, more liquid has been converted to vapor now, right? More liquid has been converted to vapor. But the thing is, there's still the liquid. There's still the liquid with the vapor. So we can say still saturated. But the thing is, new water vapor molecules have come into the expanded volume, right? But then, isn't that a problem? New things have come. But the problem is, even though new vapor molecules are getting in, that is compensated for by the increment in the volume, by the increase in the volume. So overall, the mass per unit volume stays the same. Is that clear? Right?
Yes. Yes, sir. Okay.
Just like in chemistry, all we'll be learning, like if there's an equilibrium like this, so liquid and this is the vapor. So let's say X liquid is in equilibrium with X gas. So I mean, you can think of what equilibrium constant K as what X gas over what X liquid, something like this, just a constant. So here at constant temperature, equilibrium constant does not change, right? The equilibrium constant does not change at constant temperature. So then this ratio remains the same. And the liquid concentration does not change, right? So then the gas concentration also does not change. So you can think in terms of chemistry also if you want to, but think of it holistically using physics as well. Okay. Now, vapor pressure increases as the volume is reduced and continues to do so, reaching the saturated state, right? So vapor pressure increases as the volume is reduced and continues to do so, reaching what we call the saturated state. After the saturated vapor pressure remains constant, as the saturated vapor pressure depends only on the temperature. Now let's understand this. What happens to the vapor pressure when you decrease the volume? Of course, it increases, right? And it will keep on increasing. The more I decrease the volume, the greater the increase in the pressure would be. So then what is unsaturated becomes saturated. Okay, whatever that is unsaturated becomes saturated now. Why? Because as I decrease the volume, the pressure increases, right? And it's getting packed up now, right? And then the maximum capacity to hold the water vapor is reached now. I mean, we keep on decreasing the volume, then what happens? You reach the saturated state because you cannot bear up water vapor anymore, right? You can't bear that anymore. And it starts to cry, kind of, right? That's when we say we reach the saturated state. Is that clear? And let's say you keep on further contracting the volume, further reducing the volume. If you keep on further reducing the volume, what would happen is the excess vapor, which is already saturated, starts to condense. And the same vapor density at constant temperature remains the same. Is that clear? Right? Understood?
Yes,
So you
sir.
decrease the
Clear.
volume, the pressure increases, and you reach the saturated state. Because now the molecules are getting packed up. You have a high water vapor density, which means you've reached saturated state, and you cannot hold any more water vapor in that particular volume. So then as you contract furthermore, your capacity to hold vapor is further decreasing, and then the excess vapor is going to condense. That's so beautiful. And you can see here we are thinking in terms of what? The fact that the temperature is constant, but only the volume is decreasing. If the temperature is changing, it's a different matter. We're going to get into this. Although saturated vapor doesn't obey Boyle's law, unsaturated vapor does. So let's plot a graph and see this argument. Very simple. See, now what did I say? We are thinking about what? We are going to plot the variation of vapor pressure with volume at constant temperature. We are going to see how the vapor pressure changes with volume at constant temperature. And I think we already understood the description of it, but now you're going to see. So think of a particular container where you can, you're maintaining the same temperature. And what you're going to do is now already it's unsaturated. It's already unsaturated. What you're going to do is what? You are going to reduce the volume. Now tell me, let's start from one side of the graph, pressure versus volume. So here I have a higher volume, right? I have a high volume. Here I have a low volume. Very simple stuff. So what's happening is, as I decrease the volume at constant temperature, my pressure increases. The vapor pressure increases. And the thing is, when the vapor pressure increases like that, at a particular volume, what's going to happen? At a particular volume, I reach saturated state. And then beyond that, if I decrease the volume, what will happen? Yeah, what will happen if I decrease the volume beyond that? Well, then the pressure stays the same. Now, this is because saturated vapor only depends on the temperature. Saturated vapor pressure depends only on the temperature. So this is saturated vapor pressure. Okay, so this is the curve for unsaturated vapor. Right?
So the flat line is where it starts condensing, sort of.
Exactly. So once you reach the flat line, you can see the process of condensation taking place. Okay? Right. Now, actually in Boyle's law, we learn at constant temperature, pressure is proportional to 1 over the volume. So PV is equal to constant. We'll be learning about these things in heat in the other parts. Actually, in the other class, I've done heat. That's why I thought of doing this as well. So P into V is what? A constant. So pressure is proportional to 1 over. You can understand when the volume decreases, pressure increases. And here we're thinking for a fixed mass of a gas, ideal gas, right? Thinking of a fixed mass. Of that fixed mass of a gas, right? We are saying at constant temperature, when the temperature is constant for the fixed mass of a gas, pressure is proportional to 1 over the volume. That means the pressure times the volume is a constant, which means if the volume decreases, pressure has to increase, right? But see, this behavior is only being pronounced by unsaturated vapor, because saturated vapor does not obey Boyle's law, right? So you can see pressure varies with volume, like so, showing the behavior of Boyle's law. Okay, so that's easy. And I think the explanation of it, I just gave y'all the description for the graph, and you can read it up as well. Well, so let's get into the next one. How does the vapor pressure vary with temperature constant volume? So we are going to see how the vapor pressure varies with temperature at constant volume. So we are keeping the volume constant and changing the temperature. We're going to see what's going to happen now, right? So let's think of our container where we can heat it up. So here we can see Okay, if I draw you this particular diagram, you can understand. Well, we have the liquid in equilibrium with what? The saturated vapor. So whenever you see the saturated vapor in equilibrium with the liquid, what do you see? You see, sorry, so whenever you see the liquid with a vapor, that vapor is for sure saturated vapor. Okay? So then what you're going to do is you're going to heat this up because now you're changing the temperature, heating it up. So now we're going to see how the pressure varies with temperature. Now you can see what will happen. Okay, initially it's saturated, you can see. What will happen if I increase the temperature?
There's gonna be more water vapor and less liquid.
Exactly, very good. So more liquid becomes more vapor. And in addition to that, there's more kinetic energy, as Rita and Amaya mentioned, right? So, well, as y'all mentioned again, what happened? Yeah, liquid molecules become vapor molecules because I'm heating it up, right? And then I'm adding more vapor to that volume, right? That particular volume I'm talking about, I'm adding what? More vapor molecules. And in addition to that, whatever the vapor molecules I've added, I've increased the temperature also. Ne? I've also increased the temperature. So I'm adding more vapor, and plus I'm increasing their temperature as well, which means their kinetic energy as well, which means the pressure effect is going to be tremendous. Is that clear? There's going to be an
Yes, that's
exponential
clear.
increase in the pressure, right? It's a combined effect of temperature and the mass of vapor being added. So then that means it's an exponential increase in the pressure. So we can see how it exponentiates like that. And you reach a point where you've, vaporized all of the liquid and you end up with no liquid, which brings us to the point of what? Conflict between what? Saturated state and unsaturated state. You are right in the middle, huh? It's just reaching one state from the other. So you see, the moment I go beyond a particular temperature at that fixed volume, I reach unsaturated state from saturated state, right? I'm reaching a state of saturation. Sorry, I'm reaching a state of unsaturation from state of saturation. Is that clear? Which means beyond that point of saturation, where I enter the zone of unsaturation, the gas laws are going to be valid. Pressure is going to be vary proportionately with the temperature. We'll be learning pressure is proportional to the temperature. Actually, this is the thermodynamic temperature. So you see, then this is the pronunciation. But if you take the temperature in degrees Celsius, you'll see it cutting somewhere at minus 273 degrees Celsius. So once you have done heat, they know this idea. Please go through that. I've explained. But if this is the Kelvin temperature, you plot pressure with the Kelvin temperature. So you start from here, right? In those graphs. But here, we're talking about Celsius scales. We'll be learning about those. But just have this idea that's important. And now you can see the description that I've given you. The liquid vaporized upon heating. Actually, the liquid vaporizes upon heating, and the saturated vapor increases at a high rate. Pressure actually. Saturated vapor pressure increases at a high rate due to the increase in the amount of vapor and the temperature at the same time. So because of the combined effect of both those characters, both those effects, what's going to happen? There's a tremendous increase in the pressure. It's an exponential increase in the pressure. Then the vapor pressure increases only due to the increasing temperature obeying pressure laws. Yeah, after the point of saturation, after this point of saturation, then the pressure is going to increase only due to the increase in the temperature. Because beyond the point of saturation, where we enter the unsaturated state, there is no more liquid. If there's no more liquid, there's no more water vapor being added. So if there's no more water vapor being added, the only reason for the pressure to change at constant volume is the temperature for a considered fixed mass of water vapor, right? Is that clear? Right? I don't know why people find this lesson difficult. It's a beautiful lesson, right?
It's an
So,
interesting one, sir.
yeah, very interesting, and it's very logical. You can see each and everything that we talk about is a series of logics, no?
It's
So
easy
it's
to imagine.
combined. Yeah, it's nice to imagine as well. Okay, so what is meant by boiling, right? You've heard of boiling, but did you ever question the boiling? You don't question things like that, right? I mean, the water is boiling. When did you go and question why is the water boiling? No, you're asking when is the water boiling, right? Is it over so that I can make a cup of tea, right? But you could ask this question, what is meant by boiling, right? Did you ever know? Actually, what is meant by boiling? Now, if you think, you see, of a liquid, if you want, you can think of water. You see, if you see the liquid, you see what? The vapor zone above it, right? I think now we are pretty clear about it. All right. So, and now this is the representation of what? Saturated vapor. And you can see from outside, there's this external pressure exerting itself upon the saturated vapor. So we can see that externally, the pressure is being imposed, pushing the saturated vapor down, and there's a conflict. Is that clear? There's an argument, there's a conflict there. Why? The vapor molecules create a saturated vapor because they're right above the liquid. And then from outside, you can see that the atmosphere is pushing. It doesn't always have to be the atmosphere, but rather the external pressure that imposes its effect upon pushing saturated vapor down. And there's this conflict, due to which saturated vapor remains in there at that considered temperature. And there's a zone, right? But now you think, let's get into this, explore beyond it. Think of you increasing the temperature more and more. You keep on supplying heat more and more. What's going to happen? What's going to happen? The saturated vapor pressure increases. You understood that, right? You heat it up and you are increasing the saturated vapor pressure. And now there would be a point in which the saturated vapor pressure becomes equal to the pressure of the external or the external pressure. The saturated vapor pressure will become equal to what? The external vapor pressure. Sorry, the external pressure. When the saturated pressure becomes equal to the external pressure, what happens? At that point, we say the liquid is boiling. Why? Why is that? Now you see, that brings us to the end of the conflict. If you increase the temperature furthermore, what will happen? Well, what's going to happen? I mean, if you supply heat, furthermore, what's going to happen? not the temperature, but if you supply more heat, what's going to happen? You're pushing the vapor away, right? And the vapor is now free to move. And this takes away more and more vapor. And there's a drive now, a movement forward. There's a direction to move for the vapor. And now we have reached the stage of boiling, where all of the liquid would but escape as vapor. And that's what we say. When you think about water, right? When you think about water, if you are boiling water, the external pressure is the atmospheric pressure. When the saturated vapor pressure of water becomes equal to the external pressure, which is the atmospheric pressure, and then we say there is boiling. Okay? What if the pressure reduces? If the pressure reduces, the boiling point also reduces. If the external pressure reduces, boiling point reduces. Think about pressure cookers. Inside of the pressure cooker, you have a tremendously high pressure, which means you can nicely boil the potatoes. You can have a pressure much higher than the atmospheric pressure, which means what? The boiling takes place at a substantially higher temperature. Is that clear?
That's very clear, sir.
Okay. Right. So then I've explained what is meant by boiling. So this is one of my favorite lessons, by the way. So yeah. Okay. Anyway, what is meant by boiling? Describe this taking into account the relationship between saturated vapor pressure and the boiling point. So I've already mentioned that there is a saturated region above the free surface of the liquid. This region creates what we call a saturated vapor pressure, which acts against the external pressure. When the liquid is heated, the saturated vapor pressure increases, thereby, at some point, it becomes equal to the external pressure. I mentioned that. So the temperature at which this takes place is known as the boiling point. At this point, the vapor escapes into the external environment easily. The boiling point can be increased by increasing the external pressure, just like I talked about in what you call those pressure cookers. Now we're going to get into another topic, so I'll try to finish this up soon. Hygrometry. It is the study of the water vapor content in a particular space. So you look at space and you study the water vapor content in that space. It's a marvelous topic. I used to remember, I used to give these questions, very interesting questions to some of my students those days, and then they were like thinking for days and days on end, and they were dreaming about the questions. They came up one day and they said, well, we had these dreams where we were picturing the question in our heads, and one day we got the answer. So I gave them 1 week to think a particular question, and they thought about that question throughout the week, where they told me that they visualized that question. And eventually they came up with the answer, and they were so happy. Because
So even
imagination is
I
such a...
do. When I do dream, sometimes I am the white blood cell after our biology lesson.
Oh,
That's nice. That must be a very eventful one.
Yes,
yeah.
obviously. So sometimes it'll scare me, but
What do you dream
obviously,
about the white blood cell?
yeah. So I'll be doing some. I mean, my job. I'll be functioning, and then yes, and also biology questions like the current, the waves, all those waves, the motion, and all that.
Hmm. Yeah, having that imagination in your head, no?
Yes,
Yeah,
sir.
really good. It's a skill that we have developed because imagination is much, much, much important than knowledge. Knowledge is there out in the open, right? There's AI, many tools to use, but imagination is what's lacking in most people, right? The ability to think something novel, this novelty has almost collapsed in society, right? We're just more of acceptors than what? Discoverers, no? Because there were so many people statistically on a high end, very smart people who have found things for us so that we don't have to do hunter gathering anymore. Because of that extreme intelligence that some people had, the work that they did for us, now everything is easy. So we just don't have to think anymore to survive, right? But then because of that, there's pollution, right? All this chaos and everything in the world, this harmony and all that. Because there are no problems, we create problems. I don't know where it's heading, but anyway, there's a different matter. Okay, so hygrometry. The study of the water vapor content in a particular space. So I told you about imagination. You just think about a particular space, you study it. It's beautiful, right? What is relative humidity? The moment the word relative humidity comes in, you're thinking about what? A comparison, because it's relative. But before that, you need to know the thing, what is absolute humidity? What is meant by absolute? It is the thing, right? It is what it is. Absolutely true, right? We say it's absolute humidity. What is absolute humidity?
Is it like the
It is.
minimum that's always there or something?
No, Maya, it's
Nope.
the amount of water vapor that's actually there because it's absolute. This is absolutely true, right? We say so. It's the water vapor density in some space. That's all. Water vapor density in a certain space. The water vapor density in a certain space is what? Absolute humidity of that space. Simple as that. But then what is relative humidity? To understand that, let's understand a particular diagram. Let's say in a space we have a mass m of water vapor, right? So there's water vapor of mass m in a particular space. Temperature is constant, volume is constant, say, for instance, right? Now, if you think about this temperature and the volume, you are obviously going to have a particular mass of water vapor. And is it saturated?
Not
I
necessarily.
can't precisely say because I can't see the liquid. Okay, then let's say there's no liquid. Well, then it's unsaturated. But it might, of course, be where it's a location where there's neither the liquid nor no liquid. I mean, it could be an instant where the liquid is there and not there, kind of a thing, right? In the middle. But let's assume for now, thinking about a system where it's unsaturated, which means there's a mass m, but I can have more than m. Is that clear? I can have more than m, which means it's not saturated, it's unsaturated. This is unsaturated vapor. Unsaturated vapor. Now tell me, if I think hypothetically about the same volume and the same temperature, I can think of the mass that I should really have to saturate it, right? At the same temperature and the same volume, there's going to be a particular mass m of what? Water vapor that is required to saturate that particular space at that particular temperature, right? So, and then I can represent that. The same temperature and the same volume, same temperature, same volume, I'm going to have what I call a saturated mass. That's ms. I'm requiring to have a saturated mass ms. Mass required to saturate that space at that temperature and at that volume, right? Okay. Now tell me, how do I define relative humidity? I'm going to compare the amount of water vapor that I have right now in that space to the maximum amount of water vapor I can ever have in that space, given into account the conditions of temperature and the volume being constant, right? That means it's a ratio of the mass that I have in my space divided by the mass that I need to saturate that space. If I multiply this by 100%, you can see I get relative humidity. And that is the definition of RH, relative humidity. I'm going to divide. Is that clear, everybody?
That's clear, sir.
I'm going to divide up and down by V. M over V, MS over V into 100%. This M over V means what? Density of the water vapor that's available in that given space. That's the water vapor density I have in my space. So that's rho. But what is MS over V? That is the water vapor density that's there at what? Saturated state. Rho S. If I take rho over rho S and multiply by 100%, I am going to get a relative humidity. Same thing, right? Now, you'll be learning actually, some of y'all will be learning, some of y'all are very new to Elvis, so y'all will be learning deeply that PV equals nRT, pressure, volume, number of moles, R is the universal gas constant, and T is the temperature. Now, if you divide, now see PV, what's number of moles? Mass over molar mass into RT. So here I can take pressure equals mass over volume, RT over capital M. This is density, right? It's density. Okay. Then you can see P equals rho RT over M. So can you see if the temperature is constant and the same type of the gas is there? R is anywhere constant. So that means what? Pressure is proportional to the temperature, right? Pressure is proportional to density. If the temperature is constant, molar mass is constant, then what can we say? The pressure is proportional to the density, which means I can replace density in this equation with pressure. So I can write relative humidity is equal to what? Pressure in the given space divided by what? The pressure that I require to saturate the space, and I'm going to multiply that by 100%. Actually, this is the partial pressure, P, of the vapor at a given temperature. So what is PS then? The saturated vapor pressure that I should have at that temperature to saturate it. Is that clear? Everybody? Can I go
Yeah,
ahead?
sir, it was clear. Yeah, yeah.
Yes. So, sir, relative humidity, it goes for the mass, density, pressure, and all of that.
Yeah.
Okay.
Yeah. So now we're going to look at the last topic where we are going to cover up humidity. Right? It's very short kind of a lesson, but in fact, it's not short. It's a way you understand it. Because there are very good questions from humidity that we are going to discuss later. So what is meant by the dew point? It's a very deep idea, but you can think of it simply actually. If you think of the space around you, now when do you all notice dew forming? When does dew normally form?
When it's cold.
Yeah, like how? Okay, tell me. Let's say you are spending the day from, let's say, 2 o'clock in the afternoon, and wake up in the morning, next day. At what time do you normally see dew?
Early morning?
Early morning. And can you now compare the temperature of early morning to the temperature that you had before, and from 2 o'clock in the afternoon to the temperature that you have in the morning?
Much less hot. Much less temperature.
Yeah. So what happens then? Now the temperature drops means what? The capacity to hold water vapor decreases. Now see, we talked about that. Remember, if I have a higher temperature, I can have more water vapor. If I have a lower temperature, I have a lower capacity, so I can't hold that much vapor. Which means what? Air temperature then in the morning, where you see dew, it reaches what we call the dew point, where the water vapor starts to condense. So it will condense on cool surfaces by releasing heat. The water vapor, they condense on cool surfaces by releasing heat to those surfaces. Right? Like, grass, we have seen in grasses, right? And also cars, we have seen these things now, windows, right? Yeah. And of course, it also depends on the amount of water vapor that you have in the atmosphere as well, and region specific as well. So, and also it could also be a variable. So there are so many variables, but just get the idea, right? But when we define it, actually, proper definitions of these are thermodynamics. But let's make it simple so that you all will understand at your level. What is meant by dew point? Before that, you need to know this equation. Relative humidity is what? The pressure that you have in your space divided by the pressure that you need to saturate that space at that temperature multiplied by 100%. Now tell me, you just consider a particular, this is actually vapor pressure percent. Consider a particular vapor pressure percent at a temperature T. Consider a particular vapor pressure percent at a temperature T. So let's say at a temperature T, you have a pressure, what? P. So you're thinking normally this temperature that I'm talking about, that we're going to think about now together, is the room temperature. At the room temperature, we have a vapor pressure of how much? P. If this vapor pressure becomes equal to the saturated vapor pressure at another temperature, that temperature is known as the dew point, right? So just think, right now the pressure that I'm having is actually not sufficient to saturate the environment, right? Or the particular space I'm talking about. Is that clear? But at a lower temperature, actually the pressure that I have right now is enough to saturate that environment. Is that clear? So let's say I need a pressure of 2 times something, but I have 1.8 times something, the pressure. Well, at a higher temperature, I need more of a pressure to saturate. But at a lower temperature, the pressure I'm having is enough to saturate. Is that clear? Is everybody clear with that?
That's clear, sir.
Okay. So then that means I can write this pressure in special terms. What's that? What's that? What is that thing? Saturated vapor pressure at dew point, right? Because as I decrease the temperature, the pressure that I had earlier now acts as a saturated pressure. At a lower temperature, which is the temperature in which saturation takes place, the pressure that was earlier not a candidate for saturation now becomes a candidate for saturation. Is that clear? Right? Because at a lower temperature, demand is less now. So the lower pressure I'm having right now in an unsaturated environment is enough to actually saturate at a lower temperature, which means the pressure that I have right now can also be written as what? Saturated vapor pressure at dew point, because at the dew point, the pressure I have right now is enough, right? That's why we say PS dew divided by what? What is this? Normally, we are saying consider particular vapor pressure at a temperature T. So then, room temperature, there's a saturated vapor pressure. That is PS room, right? Because pressure P was not a candidate to saturate that particular space. Why? Because I needed more water vapor. But PS is the amount that I need to saturate that space. But at a lower temperature, which is, if I keep on decreasing temperature, I will find a temperature that's the dew point. At the dew point, the pressure I had earlier is enough now to act as what? The saturated vapor pressure. And that's why I say PS dew. So PS dew means what? Vapor pressure at dew point. Is everybody okay?
Yes, it's perfectly clear now as to why there are dewdrops at night at dawn.
Yeah, very good. Now tell me, what are the methods in which a space unsaturated with water vapor can be saturated? Well, if you can add more mass to that environment, you can add more mass, right, from outside to a particular volume. If you add more mass of water vapor, if you add more water vapor, you are going to a saturation, no? Because let's say in a space right now is unsaturated, in that volume and temperature, if the volume and the temperature is constant, right, both of them are constant, if volume and temperature are both constant, then at the temperature, if it's unsaturated, that means I can add more water vapor. So if I add more water vapor from outside, eventually at that temperature and at that volume, the maximum capacity to hold vapor is reached. I'm adding more and more. So eventually I can keep on adding, but the thing is, whatever that I'm adding after some point, it starts to condense, which means what? I've reached a state of saturation. Is that clear? Okay. And the other thing I can do is I can reduce the volume. Now, let's say it's unsaturated. What I can do is I can decrease the capacity to hold water vapor. If I decrease the capacity to hold water vapor, whatever the water vapor will start to condense now, because it cannot hold anymore at constant temperature, but decreasing volume. Decreasing volume means decreasing the capacity to hold water vapor. Therefore, more and more water vapor will now start to condense, right? So you decrease the temperature, you decrease the volume, you're decreasing the capacity to hold water vapor, which means water vapor will eventually condense. What happens is actually when you keep on decreasing the volume, right, you reach a saturated pressure and then it starts to condense. Is that clear? Right. And then the other thing I can do is I can add, we talked about adding vapor, right? The other thing I can do is what? I can actually decrease the temperature also. If I decrease the temperature, the ability to hold water vapor also decreases. The capacity to hold water vapor also decreases. Then what happens? If I keep on decreasing the temperature, I can condense eventually, which means I can bring a system from a state of unsaturated nature to a saturated nature by doing three different things. By adding water vapor, by decreasing the volume and decreasing the temperature. Is it all clear?
Yes, sir.
So adding water vapor, decreasing the volume, and decreasing the temperature. That brings us to the end of the lecture, right? And the next day, so what I will be doing is I will be giving you all questions. So no, I will send you all questions. Then you all can do those questions, and actually you can discuss them, right? So you all have to think about those questions maybe for 2 weeks, because next week we'll try to do surface tension. And then you are having enough time to ponder and think, you know, improve imagination to think about the things we have discussed today. Okay, right? Okay,
Okay,
so
sir.
the idea is whatever that's done today, finish it off today, right? Go into it, teach yourself, argue, right? Debate it out, and then you'll realize eventually it's a beautiful lesson. So you all have to dream about this lesson before sleeping today. Put that into your head. Okay, humidity, what did he teach us, right? Maybe you can imagine the whole lesson in your mind's eye, right? And then what you can do is you can pronounce that understanding on a piece of paper or on a whiteboard, and confirm it, because the perception of understanding is not understanding. You feel like you understand, but that is not understanding. The feeling is not the thing. You have to, if you can execute the understanding, that means basically if you can pronounce the understanding on a piece of paper, teach yourself, teach someone, that means you've really gotten it. And then with that tremendous understanding that you have, you need to get into questions. Okay? Right. Then I'll see you all next someday, right? Maybe coming Friday as well. Right.
Thank you, sir. Thank you, sir. It was a very wonderful lesson. And
Thank
your
you.
explanation was incredible.